find where we were. Okay, so I know it's, you know, with this homework, I know the last thing you probably want to do is some more derivations, so we're going to do some more derivations. Now, I promise this one isn't as bad. It's not as algebraically messy. It's actually the purpose of what we're doing today is actually to avoid all of that nasty algebra and to get more to something numerical. So real quick, just to sort of summarize and really quickly go back over what we did last time. We reviewed how, you know, energy methods got us to here, this closed form integral for a bar element. But using numerical approaches, we were able to convert to a different coordinate system and then simplify our integral with summation notation using Gaussian quadrature. So it made our life a whole lot easier. We can use this approach for any element. So what you all did on your homework assignment was this one-dimensional element. Imagine if I had you do the algebra to derive that. You would hate me. But in the end, we can do it numerically and get just as good of an answer, actually, very simply. So it's not bad. The math is very repetitive, and a lot of it's just going to be, you know, plug and chug. Again, it's one of those things that I feel that we need to go through, but I'm not going to make you all do this one by a homework assignment, so don't feel bad. Don't feel like, oh, good, we got to do this. It's not bad. Again, the concept with finite elements, the tough part is your shape functions, your N matrix, but once you get that, everything's pretty straightforward. We talked about how we convert to a different coordinate system. It makes our lives a little easier. Let's see, where we left off. Now, we also recognize this pattern with shape functions that, you know, they sum up to equal 1. They're 1 at the node of interest, 0 everywhere else. That holds true for everything except for beams and plates and shells. In other words, that holds true for everything except elements that are intended to be bent. If it's just axial deformation or planar deformation, you don't have to worry about that. So if we recognize this you know, pattern with shape functions and going from a -1 to +1 domain, we go into the world of isoparametric. So the idea behind what we're doing today, and this example we're going to do, is we're going to try and map an element to the following coordinate system. So that's actually going to make our lives a lot easier from a derivation perspective. Excuse me. I mentioned this last time. I'll sort of throw it at you again. If you remember, I sort of did my nudge, nudge, wink, wink, and I said, well, when the heck would you ever need these shape functions? Lo and behold, there were the answers to some of the stuff on your homework that you just turned in, because those are the shape functions, and they were in your handout. I know, I'm sneaky, I'm wily. So we looked at this element and we said, well, we've got shape functions for a bar that go in one direction. It's the same coordinate system across the board, so if we just multiply these, our shape functions are done, and there they are. It's actually pretty simple, pretty straightforward. There's really not much else to say. So using these shape functions, what we're going to do today, there's no, how can I put this? We really don't need much intuition with what we're going to do today. It's really just the grunt work. One thing I do want to mention, this concept of, because we're extending into 2 dimensions and extending into multiple dimensions, we have multiple stresses. Multiple stresses mean multiple strains, so now we've got constitutive relationships we need to assess. I didn't want to get too in-depth with it because we'd start venturing outside the world of finite element land and start getting more into material-related issues and things like that. I just wanted to mention the difference between plane stress and plane strain. What really makes things complicated is this, the Poisson effect. If you apply a load and you get a strain in one direction, you're going to get strains in the opposite directions or perpendicular directions as well because of the Poisson effect. Because remember, if you take a material and stretch it, it gets longer, but it also gets thinner. Okay? And that ratio is what we call the Poisson effect. That's Poisson's ratio. Now, what we do in two-dimensional analyses is we say, all right, we've got plane stress versus plane strain, and the idea is each material-related phenomenon is related to the type of analysis you're performing. If you're doing an analysis of a relatively thin section, like a plate or something like that, plane stress is the way to go. If you're doing something relatively thick, like a slice out of a dam, then do a plane strain condition, because that's what's going on. So the difference is your C matrices, they're just plug and chug though, so it's nothing very complicated. It's just when we open and operate FE map, you'll have to pick, well, am I using a plane stress element or a plane strain element? It's a function of the problem you're looking at. You need to, as the analyst, you need to be able to make that interpretation. Okay, so we've got our, excuse me, we've got our displaced shape, displacements in the x direction and displacements in the y direction against just the shape functions times the displacements. We talked about our B matrix. It's a little messier because we're dealing with strains in 2 dimensions, but ultimately it's not very complicated. And in the end, there's our strain matrix, our strain gradient matrix. From that, we can get the stiffness matrix very straightforwardly. The only thing left is our Jacobian. Remember, we're doing a change of variables, so there's that algebraic sort of leftover in the end. Again, this is all going to be fairly plug and chug in the end. We express that through a Jacobian matrix, as we discussed last time. That's basically it. What I would do is throughout this derivation, if you have your handout, just keep it on this. This is going to be what we refer to more than anything. Okay? Everybody good? I had handouts. There we go. Okay. Okay. I'm missing, or I've got 2 of these isoparametric handouts. Did anybody get? Okay, you missed. Okay, all right. Did everybody get their homework turned in? Okay. All right. Okay, so let's go through this concept of an isoparametric analysis. This isn't gonna. I really don't think this is going to be that bad. Ultimately, I think you'll kind of get the hang of it as we go through this. So, let me explain what it is that we're doing and why we're doing it. Okay. Let's consider the following. Let's consider a cantilevered beam. So we've got a beam that looks something like this. It's fixed on one end, and we'll say we've got some cantilevered load right here. Now, you all by now should be able to analyze that problem using finite elements, right? This is no different than the beam problems we did last time or a while back using direct stiffness, right? There's no different, right? You could look at it in this fashion. You could say, all right, I have a single element, you know, like so. You could say, you know, I've got a degree of freedom like this, a degree of freedom like this, a degree of freedom like this, a degree of freedom like that, right? You could cross these out because they're reactions. You know the drill, right? We could take this approach. What I want to do now is, okay, so maybe I'll, for the sake of your notes, is I'll say this is a 1D approach. Okay, so that's a one-dimensional approach. A two-dimensional approach would look something like this. Okay, a two-dimensional approach would actually be, draw out the region as a two-dimensional region like so. Take this region and actually split it up into quadrilateral two-dimensional elements, right? Something like this. Now, if we're doing something like a plane stress or a plane strain element, we're not considering rotation, right? So on each one of these, nodes, here, here, and here, like each one of these, we'd have, something like that. Oop. And then on this node, apply a vertical load P. So this would be a two-dimensional approach. Actually, instead of having line elements, actually having planar two-dimensional elements. Now, is there a purpose for doing that on a problem like this? No, not really. But what if you're trying to find the stresses in an oddly shaped cantilevered retaining wall? Or, the stresses in some mechanical planar component where the geometry is really weird. That's where the finite elements comes into play. Now, what I'm doing for the purposes of this example is I'm going to isolate a particular element. Okay? Let's say this is the element that I'm after. Okay? So my goal is write a K matrix for the shaded element. Now, note, if we were doing a three-dimensional approach and actually using brick elements, it would almost be like we actually, we would draw the beam in 3 dimensions and imagine each one of those elements as like a Lego block constructing the beam in 3-dimensional space. The more Lego blocks, the better our solution's going to be, but the longer it's going to take to run. Make sense? Now, I'm going to give you some dimensions for this element so that you all have this. So let's look at the element. So I'm going to say that this element is here's the x-axis, here's the y-axis. So this is zoomed into that shaded element, like so. And I'm going to say that this is 10 inches and this is 5 inches. Okay? Now, in order to maintain a consistent node numbering scheme, I'm going to say that this is node 1, this is node 2, this is node 3, this is node 4. Okay? Now, one thing I'm going to do is I'm going to say that for this element, we're going to say E is 29,000 KSI. We're going to say that our Poisson's ratio for steel is usually around 0.3. That's especially true for carbon steel, mild carbon steel like what we use in buildings. And then we'll say, I think for this example, I said the thickness was 1/2 of an inch. That actually, of all of the numerical properties in our analysis, that's the one that's the easiest to apply, is the thickness. Okay. Does that make sense? Everybody okay with that? All right. Before we move on, let's make sure we're all paying attention. What are the coordinates of node number 1? 0, 0. What about number 2? What? No, that's in inches. Those are all in inches. There we go. So just 10, 0. What about that one? 10, 5. Everybody okay with that? Okay. Now again, our goal is to map this to a 1-to-1 square. Okay? Everybody okay with that? All right. All right. Does everybody have all this? Okay. All right. So let's start off by looking at our shape functions. We'll do N3 over here, N4 here. Okay, so N1, the shape function is, what is this, like 1 over 4, 1 minus xi, and 1 minus eta. 1/4, 1 plus xi, 1 minus eta. And so forth. Okay. Notice by just writing them, see how they kind of follow a pattern? Y'all notice that? I mean, it's the same quantities, and it's really just a function of changing your signs. One of the nice things about an isoparametric derivation is just that, okay? It always follows that pattern, okay? Does that make sense? Now, another thing I really want you to get used to in your brain is the concept of how versatile these shape functions really are, okay? In other words, you can use them really for any interpolated value along the element. For instance, this element is defined by points 1, 2, 3, and 4, right? That's what it's defined by. If the coordinates of node 2 changed, this would be a different element, right? Make sense? Now, these 4 nodes are what define what this element looks like. My point is, okay, my point is, I know what x1 and y1 is. x1 is 0, y1 is 0, right? I know what x2 and y2 are. x2 is 10, y2 is 0. I know what x3 and y3, 10 and 5, right? What if I want to find the x coordinate right here? You know, some random point, let's say right there. How do I find the x coordinate and y coordinate of that point? And I'm sure some of you are thinking, well, just look at it, you know. That's true, but mathematically, a fair statement would be right? That's what those shape functions are. Those shape functions interpolate values within the element, right? If I know the values at the node and I want to determine the values inside, it's just interpolation. That's what it is. And similarly, the same thing for y. Oh. Make sense? Any questions? All right. Now, if we go back to our slideshow just for a minute. If you remember, we're going to have this whole Jacobian thing pop up. It's our change of variable, right? Now, in order to do that, we need to take the derivative of these x terms with respect to our new variables. And how do we do that? We just factor out our constants. Keep in mind, what is this expression right here stating? It is stating that the x-coordinate anywhere along the element is n1x1 plus n2x2 plus n3x3 plus n4x4. If I want to take the derivative of this, these x values here, they're constants. They're just the numbers that define the coordinates of that element. I can factor them out. I have to take the derivatives of these directly. Okay? So my point is, we're going to need derivatives of these shape functions in order to do this whole Jacobian and chain rule thing. Let's just go ahead and do that right now. So derivatives of, here I'll make it full screen, derivatives of shape functions. All right. So let's keep this simple, but I'm going to keep it interactive. I know it's rainy, and I know the last thing you want to do is a bunch of derivatives, but I'm going to keep it interactive. Let's start off with n1. So it's 1/4, 1 minus eta, or 1 minus xi, 1 minus eta. So let's take n1. Now I want somebody in here to tell me what is the derivative of n1 with respect to eta, or to xi. So let's look at this top term. Let's go back to calculus, partial derivatives. I'm taking the derivative with respect to this, so everything else is a constant. How do I take the derivative of this upper function of here if everything's a constant but that? Well, I factor out the 1/4, right? Factor out the 1 minus n, or eta. And what's the derivative of this middle term? What's the derivative of that? So I'll write it out. So I'm taking the derivative of that. So it's the derivative of 1/4, 1 minus eta, 1 minus xi, 1 minus eta equals. Can I factor out the 1/4? I bet it's a number. I better be able to factor it out. Can I factor this term on the end out? Right? What's the derivative of this? Come on, I know it's late, but work with me. What's the derivative of that? Say it again. All right. Look, if I hold on, guys. I think you're thinking too much about this. If I take the derivative of 1 minus x, what is that? What? -1. There we go. What is the derivative of 1 minus? There we go. So I propose to you that it's 1/4 minus 1, 1 minus eta, or, oh, okay. Is everybody all right with that? Everybody okay? All right. So help me out. What's this going to be? What's that going to be? Do you even need to do any math? There we go. There you go. You don't even need to do any math. See? I'm trying to make your lives easier with all this calculus. You do one, and then you kind of notice there's a pattern to it, right? See what I mean? All right. If I just gave you the rest of them, would you take them on blind faith? Would you believe me? Shaking your head going no. Well, do it yourself. All right. So what I'll put is after a bunch of derivatives, we get the following. So if you do the N2s, you're going to get, with respect to xi, I've never been good at writing that letter. What do we get 1 minus eta over 4. We get minus xi minus 1 over 4. And then tried to do it a little color-coded so that you all can tell the difference between what I'm doing. These are all the N3s. And here's all the N4s. Minus eta minus 1 over 4. Okay. Everybody with me so far? Okay. Help me out with a couple things then. Can I extend this down a little bit? Is that fine? Okay. For our element, I'll say for our element, so would it be a fair statement to say our x coordinates are 0, 10, 10, 0, and our y coordinates are 0, 0, 5, and 5? Is that fair? Is that okay? Everybody good with that? Now, okay, if you're good with that, let me know. Am I all right to go back to the PowerPoint for a little bit? Am I all right? Okay. Now, okay. Actually, that's not the slide I want. I want this slide. Okay, if you recall, what we're trying to do is this. We're trying to take this element of any random geometry, which this is from, like for our element, like this is 0. Come on in. This is 0, 0. This is 10, 0. This is 10, 5. And this is 0, 5. Right? Okay? Right? Now, what I'm trying to do is I'm trying to map this to a -1 to 1 coordinate system. Okay? So in order to keep things simple, I want to evaluate this. For our example, this is just for our example, I'm going to pick a really simple point. Okay? The point I'm going to pick is 1/2, 1/2. Okay? Just to keep things simple. All right? Is everybody all right with that? Now, let me explain what I'm doing here. So maybe I should put on the side, let's evaluate for xi is 1/2 and eta is 1/2. Now, when we actually do this for real, like when we really do this in the world of finite elements, we're not going to do this for eta equals 1/2 and xi equals 1/2. Let me be very clear about this. Dr. Michelson right now is picking 1/2 and 1/2 because those numbers are nice, pretty, easy to calculate numbers. The numbers we're really going to use when we really do this in real life are going to come, if you don't mind, are going to come from here. When we really do it, we really care about evaluating these terms at our Gauss points. Okay? I'm not doing that right now because the numbers would get messy. Okay? So I just want to demonstrate how these calcs work right now. Okay? Is everybody all right with this? All right. So really, if I wanted to do this, you know, according to Gaussian quadrature, I wouldn't do 1/2 and 1/2. I'd do 1 over the square root of 3 and 1 over the square root of 3, but I'm trying to avoid decimals. All right. So real quick, before we move on, can anybody tell me where this is on the real element? In other words, watch this. Here's the element that we're considering, right? And we're trying to go from a coordinate system that's -1 to +1, right? So if I was to try and draw that out, like this might be a xi of -1. This would be a xi of +1. Maybe out in the middle, that would be xi of 0. That would be xi of -1/2. That would be +1/2. Do you see where I'm getting at? Remember, our coordinate system, we're going from -1 to +1, -1 to +1. So would it be a fair statement to say that this corresponds to x equals 7.5, y is 3.75? Do you all see how I did that, or did I just pull that out of the air? I mean, you tell me. Let me do that a little better. Are you all okay with that? It's a rainy day, and I feel like they're getting a little glassy. Is that, you tell me. Think the element, we're mapping it to go from -1 to +1. So, like, this would correspond to -1, this would correspond to +1. So if this is -1 and this is +1, what's a half? It's about 7.5. You see that? If this is -1 and this is +1, and we're talking about a half, that's about 3.75. I'm just trying to make sure that you see where I'm evaluating this. Again, I picked 1/2 because that's a nice, pretty fraction. But really, what we care about are the Gauss points. Okay? Everybody all right with that? Okay. All right. So, what was I doing? Okay. Let's go back to these derivatives. All right. Okay. Let's talk about that first one. What was that first one? It was the derivative of n1 with respect to xi. And you told me it was that, right? Isn't that what we got? This is our point of interest, right? 1/2 and 1/2. So that would be that'd be that, right? Is that a fair statement? Is that a fair statement? What about the next one? The next one is, what is it? It's gamma n1 with respect to eta, and that's, is that going to yield a different value? It's the same value, right? Make sense? Just plug in 1/2 minus 1 over 4. Am I going too quick? Everybody good? Okay. All right. So would you be all right if I just showed you the rest of them? It's just plug and chug, right? So if I do n2 and with respect to both variables, I get positive 1/8 and minus 3/8. What do we get here? Positive 3/8 and positive 3/8. And then the last one, all right. Is that good? Is it all right that I just sort of gave you that? Or you tell me, could you all come with that on your own? Okay. All right. Now, okay. All right. So, let's now look at the Jacobian. Okay. So, let's sort of take stock, because I feel like we've done just a bunch of math and derivatives. I really want to make sure that you all understand what we're doing and why we're doing it. So, we've got this example element defined. It's 10 inches wide and it's 5 inches tall. So the first thing that we did is we want to define what is x and what is y at any random point, and more specifically, what are the derivatives. The reason why is because when we're converting from this x and y coordinate system to a isoparametric coordinate system from -1 to 1, we got to do our variable substitution, and that's what we're doing here. The difference is that when what you all did for your homework and what you all did for the bar elements and things like that before, everything was in terms of x. The nice thing about doing this in terms of these new variables is look at how the variables are kind of going away. We don't have these massive, ridiculous expressions that you all hated on your homework, you know, doing all these integrals and alphabet soup going crazy. We're dealing with 1/8 minus, it's a number. Do you see what I mean? It's something that these things will really like. That's the whole point, okay? Now, in order to do this appropriately, we got to deal with that change of variables from one system to another, and that's where this Jacobian comes into play. And you're going to find it's a really nifty result in the end. So what we need to do is we're trying to determine that change of variable. So we're trying to determine the derivative of my one coordinate system with respect to the other. Now, the math says what I do is this. x1 times the derivative plus x2 times the derivative. And a derivative. The nice thing about all this is that all the symbols, they're all starting to kind of melt away. Watch this. What is x1, x2, x3, and x4? Those are the coordinates of the element, right? So 0, 0, 10, and 10, right? What are these derivatives? 1/8, or negative 1/8, 1/8, 3/8, minus 3/8. You see this? All right? Well, the final answer won't be 0, but I do see why you think that. Because x1 is 0, and this is minus 1/8. Plus x2 is 0, this is plus 1/8. x3 is 10, this is plus 3/8 plus 10 minus 3/8. Actually, is this coming out to be 0? Or did I type something out wrong? Let me see something. What's that? No, it's 0, 10, 10, 0. There we go. Let's see. I did something wrong there. This one is 0. That one is 10. I was going to say, I did something wrong there. Does everybody see that? All right. So what do we have here? We have 10/8 plus 30/8. What is 10/8 plus 30/8? That's 40/8 or 5. Does everybody see that? Is everybody okay with that? Okay. Therefore, watch what I'm going to do. Therefore, the Jacobian, or the Jacobian matrix is the following. And then, I'm trying to remember which one it is. Give me one moment. This one I know is y and eta. Y. Oh, goodness. I need to get better at that. And this is x. Now, if we look at this Jacobian matrix, really we just need to do each one of these terms, right? Okay. This one we already have. That one's 5. Okay. Would you believe me if I just filled in the others? Everybody all right with that? This other one, this one is 0, this one's 0, and this is 5. Whoa. 5 halves. Okay. Are you okay with that I just gave you these numbers? Everybody okay with that? Somebody tell me then, what is the determinant of this matrix? Can anybody do that in their head? What's the determinant? 25 divided by 2, or 12.5. Make sense? All right. This, I know you're probably like, so what? There's actually a very interesting physical reason why that number came out to be 12.5. One of the interesting thing is, I could have told you that number was 12.5 without doing any math at all. And I'll explain why. Okay. Why are we doing all of this right here? The derivative of one variable with respect to another. Why are we doing that? We're doing it because we want to do a change of variable, right? We want to change from this x and y coordinate system to this more natural coordinate system, from -1 to +1. And I said the reason that we do that is because of a process that we term mapping, okay? In other words, we are trying to convert this element into that element. Now, for what are the dimensions of our element right now? They're 10 inches wide and 5 inches tall, right? Now, this mapping concept, I propose to you that really what we're doing is shrinking the element down. What's the area of the element that we're dealing with right now? What's the area of it? 50, right? 10 times 5. What is the area of this element? 4, right? It's 2 inches, or 2 wide and 2 tall. All right? We shrunk our original element down to this element. By how much of a factor? 50 over 4. What is 50 divided by 4? It's 12.5. Okay? That number, I know the determinant of J seems like, who cares? That's actually one of the critical terms in our stiffness matrix. Now, technically, we didn't really need to do any of this math for an element like this. We can just look at it and go, oh, it's 12.5. We need to do all the math to derive the stiffness matrices, or the B matrices, what we've got here. But in the end, I wanted you to see what this Jacobian represents. Remember, let me go back up here. Remember this. This was our bar element, and we went from a original mechanics-based coordinate system to a natural -1 to +1 coordinate system. And I told you that there was going to be a pile of junk left over from that coordinate system. Another way of thinking about it is that pile of junk is a scaling factor. It's, the scale of the one coordinate system versus the other. For us, where we're doing this mapping, because our original element was really big, really what we did is shrunk it down. How much did we shrink it down? A factor of 12.5. So it's funny when we calculate our stiffness matrix, when it's all said and done, we're just going to directly multiply that stiffness matrix by 12.5 because that's sort of our scaling factor. That's kind of what a Jacobian is. So I know we did all this crazy math to get there, but it's kind of validating that what we're doing isn't way off the wall stuff. Okay? All right, let's see. All right. Last thing I want to show you, and then I want to pull up my Excel sheet, is the B matrix. Now, what I've got here is my B matrix in terms of xi. Okay, in terms of xi, and in terms of eta. So B, it equals, what is it? I mean, you have it here in terms of x and y. See, this is the B matrix in terms of x and y, right? And again, it's just a function of the strain. What I'm going to say is that instead it's a function in terms of these new coordinates. So N1 x, and then, here I am saying it and then I'm not doing it. Good, I cannot write this symbol for the life of me. There we go. And that's supposed to be 2. And 3. Four. And then 0 and 1 over eta. And so on and so forth. You all see the pattern? Okay. So if I extended this out, I'd have a B matrix that instead looks like this. Now, keep in mind, again, I know we've got a bunch of symbology, but ultimately this is all numerical. What is the derivative of n1 with respect to xi? We already done that. It was minus 1/8, right? Minus 1/8. There's no symbology. This this B matrix is now a number. It's minus 1/8, 0, and then plus 1/8, 0, and then 3/8, 0, minus 3/8, 0, and then 0, minus 1/8, 0, 0. And I'm just sort of filling in the pattern. You all are looking at it right there. So. Yep. Okay. In the meantime, did you all get that email I sent you with the Excel sheet? If you haven't opened it up, go ahead and open it because I want to pull that up and actually look at some things in that sheet. Don't worry, I'm not expecting you all to create this, especially since I gave it to you. So, and I'll give you a minute. Does everybody have this written down? Okay. Now, okay, so, oh, it's a 1/4 of an inch. I said the thickness was a 1/2 inch, and it's a 1/4 of an inch. Oh well, no big deal. It doesn't really matter. Okay, now let's go through this. So I've got 2 sheets. If you notice on the bottom, I've got a parameter sheet and then the actual stiffness matrix. Okay, so my element coordinates. See where I got those? That's just the coordinates that define the x and y of the element. Okay. So 0, 10, 10, 0, 0, 0, 5, 5, right? Okay, the element thickness, we'll say it's a 1/4 of an inch. It really doesn't matter. It could be anything. Material parameters. Now, for this problem, I'm assuming plane stress conditions, and I'm doing that because what we were doing was a beam analysis, and we'll say for the purposes of our example that beam is relatively thin. So plane stress makes sense. How am I calculating these? It's plug and chug from the PowerPoint. So, enable editing. So this first one is E over 1 minus nu squared. This is nu times E minus 1 over nu squared, and so on and so forth. And that's G, or E over 1 minus nu squared times G. Okay. For the purposes of this example, I'm going to do 2-point integration. So let's have a pop quiz. All right. 2-point integration. This is technically a double integral because I'm integrating across the x-axis and across the y-axis. So how many terms am I going to have? 2-point integral evaluated for 2 integrals. Remember that? You take the number of Gauss points, raise it to the number of integrals. Y'all remember we did Gaussian quadrature not too long ago. If I have let's back away from this. If I have a 4-point integral and I'm doing double integration, how many terms is that? 4-point integral, double integration. Oh, it's 16. Remember? Remember, it's like 1, 1, 1, 2, 1, 3, 1, 4, 2, 1, 2, 2, 2, 3, 2, 4, 3, 1, 3, and so on and so forth. Remember that? Everybody with me? So how many terms am I going to have in this evaluation? 4, right? Does everybody see that? So what you see on the next page, I know it seems like a mess, but look at this. I've got this split up into columns. All of this is my first term. All of this, my second term. All of this, my third term. Do y'all see that? Okay, so look at this. So point 1, look at the indices up top. So look at my Gauss points and see how I cycle through all of them, all the permutations. See, it's like that Gauss integral we did, it's just blown up a little bit. So based on these assumed values, now remember for the example that we just did, we were looking at plus 1/2 and plus 1/2. We're not looking at that here. We're looking at negative 0.577 and negative 0.577. Hence why we didn't use this in the example. We did it, you know, with a little bit more of a cleaner number, something that would come out a little easier. So let me zoom into this first index. So here's my weighting functions. Here's my Gauss points. Shape function derivatives. How am I calculating these derivatives? That's at like eta minus 1 over 4 and xi plus 1 over 4. Those are those symbology terms that I derived. Here's the element coordinates. Here's the coordinate derivatives. Notice how, again, look at this coordinate derivatives. Notice how, regardless of what these values were, I still get 5, 0, 0, and 2.5. Why? Because I don't care where I evaluate this term at. It doesn't matter because the element still has an area of 50 square inches, and the natural isoparametric element has an area of 4. So that scaling factor better be 12.5 regardless. Make sense? Here's my B matrix. Here's my C matrix. Beta transpose CB. I know that's just a big matrix multiplication, but it's something you can do in Excel. And then how do I calculate the actual stiffness matrix? Well, I got to multiply it by my weighting functions in Excel, my weighting functions, beta transpose CB. I have to multiply it by J because that's a scaling factor. And then I have to multiply it by the thickness. Okay? So I get a stiffness matrix for that term. Do it all again. So that's my stiffness matrix for index 1, 1. Then I do index 1, 2. All right, so let me zoom out. It's actually probably easier to see when you zoom out. So to give you kind of a scale of what we do in finite element world, this is that first index. This is that second index. This is that third index. This is that fourth index. Sum them up. This is the actual stiffness matrix for that element, right? Make sense? Keep in mind, and this is, I want you to really kind of grasp the scale. We were only talking about that one little element in the whole problem. That one little itty bitty element. You have to do that for every single one of these. That's the power of some of these finite element analyses, right? Think about that. Like, go back to the very beginning of the PowerPoint that we dealt, or the PowerPoint that we used this semester. Look at some of these applications I was showing you. Look at this. All right, look how, just imagine, look at each one of those little elements, and it's got to do that. And these are shell elements, so the stiffness matrices get a lot bigger. I mean, let's sort of bring it down to scale a little bit. A two-dimensional analysis of a slope failure. These are triangular elements, so they're 6 by 6 instead of 8 by 8. But this program has to do that for every single one of these elements, every one of them. assemble it, then solve for the displacements. That's a lot of math. But again, what do these things love to do? They love to count and they love to add. Okay? Make sense? All right, I know it's probably a lot, you know, to sort of grasp on you know, just after you've done this. But again, just the scope of what these programs are able to do, it actually is pretty impressive. Everybody good? All right, that's all I have for you all, guys. I will see you all next time.